right, I've had some questions on the dot product from some of my SL students, and so I want to talk through a few things. If you hear violin playing in the background, my nephew is downstairs practicing, so I hear his metronome, and not sure what you'll get to hear, but if I get distracted, that might be part of why I get distracted. Okay, so on this one, first of all, we don't talk about multiplying vectors in general because there's actually two ways to multiply vectors. So we can multiply, and so if you just say multiply vectors, that's not clear. So you need to be able to, you need to say we're either going to take the dot product or you're going to learn soon the scalar product, or I lied. The dot product is also known as the scalar product, and the vector product is also known as the cross product. Okay, so dot and scalar product are the same thing, vector and cross are the same thing. And so what happens is when you find the scalar product, what you're going to end up with is a scalar. And when you find the vector product, what you're going to end up with is a vector. Okay, so we can't just say multiplying vectors. The next thing here, so to find the dot product, I hope you remember how to do that. Let me do that really fast. If I have a vector, well, let's just go 1, 2, 3 times, and we're going to dot it with a vector, I don't know, -2, 0, 5. The way that we do the dot product is we multiply, 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 and then add those values. So 2 times negative 2 times 1 is -2, this plus is 0, and this becomes plus 15. So the scalar product of these two vectors is equal to 13. That's a scalar. We're done. Okay, and so there was a problem. I think one of the questions was trying to understand what the book is going for in this problem. Well, what happens is when we take the dot, they're trying to say it doesn't matter if we do A dot B or B dot A, they end up being the same. Well, okay, so let's see. When I take the dot product of this is equal to A1 B1 plus A2 B2 plus A3 B3, which is the same thing as saying, well, A1 times B1 is the same thing as saying B1 times A1 plus B2 times A2 plus B3 times A3. Okay, so all of those are the same, which is the same idea as saying, okay, B1, B2, B3 dotted with A1, A2, A3, which is just B dot A. So notice this is kind of like how we would do our trig identities or our proofs. We started on one side and we kind of manipulated it and got down to the other. So that's their whole point, that I can say A dot B or I can say B dot A and it's going to give me the same thing. No. The next one, what we have here is they wanted to show that if I take a vector and dot it with itself, I get the magnitude squared. Well, let's see. If I have A1, A2, A3 dotted with A1, A2, A3, this is going to give me A1, well, squared, plus A2 squared, plus A3 squared. Well, notice the magnitude, this is just this is the square root of something squared, right? The square and the square and the square root would cancel each other out. So I can notice what I've done here is I've just taken the square and when I square and square root the same thing, like, or if I square it and square root it, those operations kind of cancel out. The trick is that positive and negatives do weird stuff, but the squares take care of any negatives anyway. So sorry. This is the magnitude of vector A, and that's been squared. So those work like, so the whole point is, okay, check out this cool little property. The dot product here gives us, the dot product of a vector with itself is equal to its magnitude squared. So the reason that we care about this, and hopefully you watched that other video, I made this nice long video about how we come up with the fact that we can find the angle between two vectors. So if this is vector A, and this is angle theta, and this is vector B, we can find this angle by saying cosine of theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B. Okay, I have this seems like, okay, how in the world did you get there? But I have a video to show you. It uses the law of cosine, and you kind of have to expand things out, and then kind of things will clean up, and it simplifies, and it's beautiful. And I don't want to repeat that here, but that's what's happening. So really and truly, why do we care about the dot product? We care about the dot product because it helps us find the measure of the angle between two vectors. And in particular, well, what do you know? Cosine of, well, what happens if, what values give you a cosine of 0 degrees, or maybe I should say cosine of theta equals 0 radians? Well, in order for, if you think back to your unit circle, which never goes away, have you noticed? On the unit circle, cosine's the x value, so x is 0 here at pi over 2 and there at 3 pi over 2. Okay, so if I have a vector and another vector and I want them to be perpendicular to each other, what I'm going to find is that this cosine value equals 0. Well, in order for cosine to equal 0, this whole thing right here has to be 0. Well, that means that my numerator really needs to be 0 because I don't care what my denominator is. And assuming that these are actual real vectors, they're not going to have a magnitude of 0, because if you have a vector can't have a magnitude of 0 because it's no longer a vector. It's now just a point in space. So what happens here is if we take the if we take the dot product of two vectors and we get 0, then this whole thing goes to 0, which makes this whole side go to 0, which means that our angle has to be 90, or it could be 270, but basically we're going to have a vector here and a vector there, or, well, I mean, you could have a vector here and a vector there, but this angle is 270 or that angle is 90, however you look at that. So hopefully that's clear, and that's why we care. So like if I want to show, oh, and by the way, so we can call that perpendicular. We also talk about it's a normal vector. A normal vector means that it's perpendicular to whatever we're describing. And another word is, I can't spell, orthogonal. That's an R, orthogonal. I think that's right. I'll have to go look that up. If you see, show two vectors are perpendicular. Well, okay, what we need to do is we need to show that their dot product is 0. Show that a vector is normal to another vector. Normal means that it's perpendicular, so then we'd show that the dot product is 0. Show that vectors are orthogonal to each other. Okay, we show that their dot product is 0. And that's why we care about the dot product. It seems like we're just doing math for no real benefit, like if I do something like this, well, why do I care that the dot product is 0? I don't until I think about, okay, now I want to find, so if I've got these two vectors and I want to find the angle between them, I could say cosine of theta is equal to the dot product, 1, 2, 3, dotted with negative 2, 0, 5, over the magnitude, this is 9, plus 1 more is 10, plus 4 is 14, that's 25, plus, that's 29. So the inverse cosine of, what did we say? This was 13 over, okay, and here I'd need a calculator, and I didn't bring one home, so this is going to be an interesting teaching experience with me not having a calculator, but here we go. So I hope that helps. So big takeaway, we don't talk about multiplying vectors because we're going to have two ways to do it, and there's different properties that we can demonstrate with that. So there's more of them. I expect HL to know more of it than I do with SL, but hopefully that was clear. Let me know if there's any way I can be of further assistance.